Okay, good morning everyone. So in today's lecture I am going to cover two different topics, namely the topics on broken extremals, and in the later half of this lecture course I am going to talk about the Hamiltonian formulation of the necessary condition for extremals. Okay, so in today's lecture we are covering the topics of broken extremals, and in particular I am going to cover the topic of in broken extremal I am going to introduce the famous Weierstrass-Erdmann theorem. The Weierstrass-Erdmann condition. Okay. And also the second half of this lecture will introduce the Hamiltonian formulation of, which is an alternative formulation of the Euler-Lagrange condition. Okay. So let me start the first topic. So so far what we have seen is we have found the extremals of several different types of functional, but the underlying assumption of those extremals are that they are at least continuously differentiable up to order 2, if not then higher. So today in this lecture we are going to relax that criteria and we will assume that the extremals are continuous but may not be continuously differentiable. So far the assumption is, so we assumed extremals have at least two well defined derivatives. The extremals have two well defined derivatives. So we are, as I said, we are going to relax that assumption today. Okay. So this is not, I just want to quickly give an example saying that there are several examples in this case of broken extremals or extremals which are not continuously differentiable. So not always true, right? And the example that we have in mind is the example that we have already seen in our lecture 3. So students should recall the example in geometric optics where we found the optimal path that the light ray covered while following the Fermat's principle. Okay. So that was the example in geometric optics. So please recall that example, geometric optics. Okay. So there in that example we found out a very easy way of finding, well, very a way which did not involve any particular result, a very easy way of finding the an extremal which was not continuous in its derivatives. But we also promised towards the end of that example that we are going to derive the general conditions. So in this lecture we are going to do exactly that. Okay. So before I derive the general conditions for broken extremal or the Weierstrass-Erdmann condition, let us look at what is the significance of finding these conditions, or what sort of extremals belong to this broken extremal category. Well, one quick example is there are several innocent looking functionals in which the extremals are not continuous at all. Forget about discontinuity in derivatives, they are not even continuous functions. So some problems don't admit smooth extremals. So the problem that I have is we have to find y of x to minimize this functional f of y which is given by integral minus 1 to 1 y square 1 minus y prime whole square dx, right, and subject to y of minus 1 is equal to y of 1 is equal to well, I have two different boundary condition, y of minus 1 is 0 and y of 1 is 1, right. So, it seems that we can quickly find the extremal by through the Euler-Lagrange equation. Let us see what happens. So, we can see that for this integrand f, it is purely a function of y and y prime, and there is no explicit dependence on x. So, to find the solution, we can directly use our Beltrami identity, saying that h, which is y prime f of y prime minus f, is a constant, right. And when we plug the value of f, I get that. So, I get the following. We plug the value of f and we get the following expression: y square 1 minus y prime square is equal to C1, which is our constant, right. So, let us try to solve this problem. We could to show the solution to this problem, let us first assume that the constant on the right hand side is 0, right. We will look at the case, general case, later on. So, case when C1 is 0, right. If C1 is 0, then I have the solution to the Euler-Lagrange equation as the following. So, this is equal to 0, or I am saying that y is 0, or I have y prime is equal to 1 plus minus 1, and this gives me y is equal to plus minus x plus a constant a, right. So, either the solution is a constant which is 0, or the solution is a straight line. And further, I have two conditions. Note that y of minus 1 is 0 and y of 1 is 1, right. So, note that the first solution does not satisfy both these conditions. So, I am going to discard. So, this is not the solution that we are after, but notice the second solution. So, if I take y of minus 1 equal to 0, let me just assume students can check that even this solution does not satisfy both the conditions. So, the conclusion here is neither solutions satisfy both boundary conditions, right. So, I have that y of minus 1 is equal to 0 and y of 1 is equal to 1. So, both boundary conditions are not satisfied simultaneously by neither of the solutions. So, let us now look at the case C1 not 0, right. So, in that case I am going to rewrite this expression and write y prime as a function of the constant C1 and y. So, I get that this is also equal to 1 plus minus 1 by y square root of y square minus C1, right. And when we solve that, we get the following solution, which is y minus C1 square, well, y square minus C1 is equal to x minus C1 whole square, which is which if you draw the curve will be a rectangular hyperbola, right. Okay. Well, we have a two constant family of solutions. So, we have C1 and C2, right. Now, the expectation is that constant C1 and C2 can be found through the boundary conditions that is present. Now, note the following. Let us draw this hyperbola. Well, so first of all, let me find C1 and C2. If we plug y of minus 1 is equal to 0 and y of 1 equal to 1, I immediately get the constants C1 to be minus 9 by 16 and C2 to be minus 1 by 4, right. So, and so my equation is y is equal to x plus 1 by 4 whole square minus 9 by 16. Okay. So, now if I were to draw this figure, let us see what this figure looks like. So, we will have, it is a rectangular hyperbola, it has two branches. Notice that minus 1 comma 0 is here. So, this is my point 0, which is minus 1 comma 0, the first boundary point, and notice the second point is 1 comma 1. 1 comma 1 lies on the second branch, and there is no way we will have an extremal which joins these 2 points, because they are lying on 2 separate branches, right. So, the conclusion here is that the boundary points are on opposite branches. The boundary points are on opposite branches, and it implies that there are no smooth extremals, connecting P0 and P1, right. It is quite clear from the diagram. So, which means that this problem is not going to admit any continuous solution, let alone continuously differentiable solution. So, that is why we look for the broken extremals, right, or the condition through which we can at least find extremals which can connect the boundary points, which are at most piecewise continuous, right, piecewise continuously differentiable. So, the broken extremals, so typically I will have the following figure for broken extremals. So, let us say I am drawing the extremal y as a function of x, and my starting point is x0, y0, and my ending point is, let us say, x1, y1. My broken extremal could be the following, like this, right. So, here at x star I have the so called corner, right. So, the broken extremal, although we are going to deal with continuous broken extremals, but they will not have derivatives, or they will have not defined, the derivatives are not defined, at least at some finite number of points. We call those points as corners. So, in broken extremals we look for continuous functions, and we try to minimize corners. The less the number of corners, the better it is for us. Okay. So, this question is, notice that Euler-Lagrange equation gives us the extremals which are continuously differentiable, the way how Euler-Lagrange equations are derived. This question is, are those class of continuous or continuously differentiable functions also extremals over a class of functions which are piecewise continuously differentiable, right? And the answer is yes, and it is given in the form of a result which we state it in the form of a theorem. So, the theorem says, it's theorem 15, if a smooth curve y, by smooth I means that the required number of derivatives exist, of y gives an extremal of a functional f of y, gives an extremal of a functional f of y over the class of all admissible curves, in some neighborhood of y, of y, right, gives class of admissible curves in some neighborhood of y, then my function y of x gives extremals of f of y over the class of all piecewise smooth curves in the same neighborhood. Right, the same neighborhood, or in short, I can say that the necessary condition for extremals can be extended to the class of piecewise smooth curves. Okay, so the necessary condition, this theorem says that the necessary condition for extremals can be extended to piecewise smooth curves. Okay, so our Euler-Lagrange equations will still work. Now the second question that we ask is, if that is the case, the Euler-Lagrange equation works, how are we going to find these broken extremals? So let me show you how we are going to find these broken extremals. So let us look at in another slide. So this question, the second question that we have asked is how to find these broken extremals. Okay. Now, so to do that, let us say at the corner point, at the corner x star, we break the integral into two parts. Break the functional into two parts, right. So what we do is we write down our functional f of y to be f1 of y plus f2 of y, which is also the first integral becomes integral from x0 to x star, over which we have a continuously differentiable solution of the integrand f of x comma y prime dx, and the second integral, the second functional is over the interval x star to x1 of the same integrand. So we have broken the entire integral at the corner point. So then, so let me draw this figure. So we are talking about, let us say, a functional of this form where this is my corner point, right. So this is x0, this is my x1, right. Okay, x0 and x1. Okay. So then the requirement is that y is continuously differentiable, up to second order, except at the corner point, except at x equal to x star, right. And further, I also require that the solution is at least continuous, which means that the solutions y1 matches with the solution y2 at x star. So they are at least continuous over the entire interval. And when again, since we are following the similar strategy of finding Euler-Lagrange, we have to set up the first variation, and that is we do by perturbing the function. Now this question is, what happens to these corner points during perturbation? It turns out that we can also change the corner points while perturbing our extremal and finding the variation in the functional. So what I said is the following: in our first variation, when we derive our Euler-Lagrange equations, the location of corner points corner can be perturbed. The location of the corner can be perturbed, right. So, we can also have a similar situation of this form, where now my new location of the corner is x star hat, right. So, we can always perturb. So, this is also allowed in our derivation. So, which means that when we write down the first variation, I see that the first variation delta f of eta comma y is limit epsilon tending to 0 of the following integral 1 over epsilon times integral of from x 0 to x star hat. So, over this integral we have the perturbed integrand y hat comma y hat prime dx, and the other one, when we take the first variation, the other one is from x 0 to x star, and over this we have the original integration of the original integrand, right, plus there will be an integral, there will be two more integrals, right, from the other interval from x star to x1, right. So, we do not, so right at this point we just ignore these two integrals to just highlight how are we going to write this difference, right. So, whatever result we find out for this difference that I have shown will be also valid for the other difference. So, that is why we ignore the calculation, of this setup, right, because it follows a similar steps as in the first two, as in the processing of the first two quantities here. So, notice, so in the last lecture we have derived the transversal criteria, right. So, as with the transversal criteria, if we notice this difference of the integral quantity, we expect that this will boil down to the Euler-Lagrange criteria. This difference plus the other difference will boil down to Euler-Lagrange criteria plus some extra terms which will not vanish, right. So, what I just said is, so as with the transversal condition, we get Euler-Lagrange equations, plus additional Euler-Lagrange equation plus additional terms, right. And those additional terms, once we simplify, will come out to be the following. Over the first interval, the additional terms are P1, the same transversal terms that we had found in transversal condition, P1 delta y minus H1 delta x, right, where my, so this is over the first interval. So, let me just highlight. So, my first interval is the following, this one, and my second interval is this following. So, over this first interval, my additional criteria is this quantity, right, set equal to 0, right, and so the additional terms are these quantities in the first variation. What I am trying to say is, we have not yet set the first variation to 0. So, I am just writing down the terms that we will obtain in the first variation. We will get Euler-Lagrange in the integral as an integral constraint plus these certain other quantities, right. Now, where my delta x at x star, the corner point, comes out, let us say that this is capital X star, and my delta y at the corner condition x star is y star, right. So, which means my Hamiltonian, my h, the function h is by definition is y1 prime partial f partial y1 prime minus f, and my p1 the momentum is partial f partial y1 prime, right. Okay. So then similarly, so I have so this is evaluated at from x0 to x star. So x star is the upper bound, right. So at this term is evaluated such that the evaluation at x star is the one on the right hand side, it is the upper bound. So similarly for the second component, for the second interval, the first variation will again give Euler-Lagrange equations plus the terms of the form minus P2 delta y plus H2 delta x, right. When I say the second interval, I am talking about this interval over which the perturbation is happening, that is towards the right of x star, right. Now notice that I have put in a minus sign in this term as compared to the previous term, because now x star appears on the left. So now x star, the value evaluated at x star serves as the lower bound, and hence the change in sign, right. So then we combine the first variation, we combine first variation terms. So I am not deriving very rigorously for the case of broken extremal, because we have done so for the case of continuous extremal, and so I am just giving some basic ideas. So variation, so we combine the first variation terms, and right now we ignore the interior, we ignore the Euler-Lagrange equations, because that needs, well, that will be true, right. So and ignoring the Euler-Lagrange equations, and that is done because we want to find only the corner conditions, right. So the Euler-Lagrange equations are very well satisfied for smooth extremals, but at the corner it is these two extra terms that will give us the necessary condition, right. So once we ignore the Euler-Lagrange equation, we get that the first variation of f will be, the first variation will be, so this is my delta f1, this is my delta f2. So the first variation is delta f1 plus delta f2, and that is also equal to p1 minus p2 of delta y minus h1 minus h2 of delta x, right, and this is evaluated at x star on the lower bound. Okay. So now the corner conditions will be such that this will also be 0, right. So the first variation becomes 0 when not only the Euler-Lagrange expression becomes 0, but also the corner condition becomes 0. Only then we are guaranteed to have extremals. So from here, so let me call this as, so this is the combined condition that we have at the corner. We could have one quantity varying independent of the other quantity to get two sets of corner conditions. So in general delta x and delta y could vary independently of each other, right. So not necessarily they are combined, and then we will have which means that the coefficients at the corner conditions would be separately 0, and hence that gives me my corner conditions, or the so called the Weierstrass-Erdmann conditions. So this is these are my corner conditions or my Weierstrass-Erdmann condition. Let me call, to begin with, let us right away say that my Weierstrass-Erdmann conditions are WE conditions. So, I am using a short abbreviation in my subsequent discussion. So, WE conditions, right. So, from here I get P1 at x star is equal to P2 at x star, and similarly H1 at x star is equal to H2 at x star, right. Okay. So, then we could also rewrite this corner conditions by approaching, we could say that H1 belongs to the is the evaluation of the Hamiltonian for the function from the left of x star, because y1 is at the left of x star. The extremal y2 is at the right of x star. So, this condition on the right hand side is evaluated on the right of x star, and similarly for the other equation. So, writing corner condition in terms of limits from left or right, I can very well write that the conditions are P from x star minus is equal to P at x star plus, and H at x star minus is equal to H at x star plus, right. Okay. So, let us